have you here today? Well, I would like to dedicate your attention to the study of a parametric family of recursive kernel estimators. However, the defining character of such estimators is that the projected value at n plus 1 depends on the estimate value at n and the last observation. So, due to this recursivity, the process won't have to be smoothed again when a new observation will be added. Hence, the non-parametric kernel predictor's performance is improved, where the time to calculate is reduced by using a recursive kernel. The main objective of this work is to establish the strong consistency of the regression and density recursive kernel estimators. Our work will be devised on these three sections: the estimation of the density and the regression, the almost complete convergence of the recursive kernel estimators, and the simulation using recursive methods. The work plan will follow this order. So, we are interested to the recursive version of the density kernel estimator. For independent data, where K is the kernel and HE is the bandwidth, other additional conditions on K and HE are necessary for our study. The construction of the density recursive kernel estimator is based on the idea of sharing the smooth parameter into two powers. Therefore, we share the HE into the two powers L and 1 minus L for L in the interval 0, 1. And in order to have an asymptotically non-biased estimators with an interval that equals to 1, we normalize them using this quantity. Thus, the recursive kernel estimator of the density is given by this. Coming even stronger, we shall refer to the problem of predicting the response variable ny from another exponential one x. The problem is tagged using a non-parametric recursive kernel approach to model this relationship, where the data are independent. M is the Boolean positive function, and F is the marginal density of the variable xi. Next, in the study framework of the almost complete convergence of our recursive kernel estimators, we need to shed light on some assumptions. On H1, we consider a kernel that satisfies the three conditions, while the assumption H2 of the bandwidth contains a classic condition in the recursive estimation and another useful one in the calculations. A third assumption H3 gives condition about the bonneted and the continuity of the function and phi plus the existence of the second partial derivatives of these two last ones. Now, I shall indicate to the asymptotic properties of our recursive kernel estimators. While this theorem presents the weights of the recursive kernel estimators of the density and the regression, and in order to achieve these two results, the proof is basically based on this decomposition. In addition to the use of the exponential inequality of the Bernstein type lemma, however, the result in the lemma 2. The within of our proof requires to confirm the previous 5 formula given above. In the beginning, we start with calculating the mean of the density recursive kernel estimators. Then it is indicated to develop the density f on x, which is possible owing to the conditions H1, H3, and H2, and the TCD leads to have this quantity. Thus, the lemma 2 as H2 holds, and the bonneted of the functions and the bonneted of the kernel and the second differential of f plus the condition H2 will give us the speed of the density bytes, which is the square of the bandwidth. Secondly, the proof of this one is analog to the first one. So, after conditioning the mean of the phi recursive kernel estimator y x equal to u, we pass by the same path to have the phi bias weight. The main idea here is to use the simplified version of the exponential inequality. So essentially we have to find two upper bounds for the delta E and its second order moment, which is associated through the bonneted of the functions m, f, key, and the second differentiable of this functions. We are therefore able to apply the Bernstein inequality to have this convergence serial and to get the proof of 1, 3, holding the assumptions H1, H2, and H3. In a similar way, we repeat the same previous calculation, but in a particular case, for ny is always equal to 1, so the formula 1,5 would be written in 1,6, thus we obtain our result. It remains only to take the proof of 1, 2, and 1, 4 to have the rate of the almost complete convergence of the density, and to take the proofs from 1, 1 to 1, 4 to construct this decomposition, and to have the rate of the almost complete convergence of the regression. Now, we're going to give a clear image about all these past theoretical results. So a better vision would be given in this graph, simulation graph. In the two first slides, you can notice that as long as the machine screen size is bigger, the mean of the squared error is reduced. Without forget the mentioning of that the L has a participant part in improving the performance of our estimator. However, the last graph shows a comparison between the different estimation methods. So you can see that the significant behavior of the kernel, of the recursive kernel estimator and the kernel estimator. That gives the advantage of using the non-parametric methods than the parametric methods. Well, concluding our work. The aim of this work is to establish the asymptotic results of some non-parametric estimators through the study of recursive kernel estimators, assuming that the data are independently governed variables. And in my given